All right, so today we're going to continue with where we left off. We've already looked at how to get stuff into a binary search tree. We've already looked about how to search a binary search tree, thus its name. But now how do we get stuff out of a binary search tree? In other words, delete, right? Remember, remember that we're ultimately trying to do CRUD, create, retrieve, update, and destroy. Update is basically just destroy and then create. So we're only focusing on those three. How do you get stuff in? How do you take stuff out? How do you retrieve stuff? So for example, let's go ahead and start with an easy one, right? What have we, how do we delete 13 from this tree right here? Well, is 13 in there? Nope. So we have to first, my first observation is that we have to find it first. Find it first. Or more accurately, find the node which stores it. So for example, when I ask how we're going to delete 12, we're going to find it right here. But if I ask how to delete 13, that means that we're going to have to search for it first by going left, right, whatever, to find the node that would have had it. We'll see that it's null in terms of Java, in which case we could throw an exception. We could decide not to do anything, no op. We could communicate that back to the calling function, which is what I'm going to do, to indicate that it had no effect. Right? So let's come over here to our Java implementation. We are online, so if you have any questions, go ahead and post to the live stream here. But otherwise, we have our add method. We have our contains method. And now I want to add our delete method. So public Boolean delete, or actually just let's call it remove, right? TX. We're going to remove an element X, okay? Now let's document this, right? Removes the given element from this tree, right? Binary search tree, if it exists. If no such element exists, it returns not null, but returns false, right? Because I'm going to communicate back to the calling function, did it have an effect on the tree, right? No, false, it did not, right? We didn't find what you were wanting to delete, and so therefore we're going to return false. The calling function can choose to ignore that return value, and that's its business, but we're going to communicate it back at least to, through the calling function. Returns true, code, true, if it had an effect on the tree. There we go. There's our documentation. So how am I going to delete, say, 13 first in this tree? The first thing I've got to do is I've got to find it. Just like if I'm going to delete 12, I got to find that. If I got to delete 45, I've got to find that, right? Et cetera, et cetera. So step one, find the node, if it exists, containing X. That sounds really familiar, right? We did that kind of like up here. But this one returns a Boolean. Do you contain the element X? And if I ever find it, right, using my comparator here, I return true. If I never find it by searching through the entire tree, I return false. So I could go ahead and cut and paste all of this code down here, right? Or I could have a forward-thinking kind of design. We saw this a lot in this current iteration of your project where lots of repeated code to insert an address when you do a store, when you do a person. Why? Put that into a function and reuse it. Don't repeat yourself. DRY, right? The DRY principle. Let me go ahead and make another function here. Initially, I'll make it public. Public tree node, or a binary tree node, T, right? Get node, containing the element X. Now, why would this be a little bit more general? I'm going to find the node for you. If I don't find it, then I'll go ahead and return null. I'm going to go, oops, that's not it. I'm going to go ahead and cut and paste this down here. Now, it's the same basic search algorithm. I start at the root, and while I'm currently not standing on, while I'm currently standing on a valid node here, I'm going to compare it. If that's the thing I'm looking for, then I'm going to immediately return it and be done with it instead of returning false or true. Down here, I'm going to return null as a signal that that binary tree node does not exist, okay? Lots of repeated code. how could I change this so that I'm not repeating code here? What I'll do is I'll get that node, right? This dot get node, right? Containing x, store it off into the actual node here, and I'll call it u, right? And now I can return true or false based on whether or not that's null, right? If u is null, then I'll return, actually if it's not null, right? I'll start with that. If it's not null, then I'll return, I found what you were looking for because it's not null, so I'll return true. Else, return false. There we go. Now that's much better because I'm only doing the algorithm once, and I've made it generic and general. Two fixes here, one small and one rather large, as far as design is concerned. If this expression is true, then return true. If this expression is false, return false. Is there a better way of writing that code? Don't write an if-else-if statement, just return that statement. You will end up returning true or false, just like you would before, but it's much simpler code. That's my first small fix. My next big fix here is, let's think about this public method. All right? Should I allow the outside world arbitrary access to the nodes of this tree? Probably not. In fact, should I even let the outside world know that this thing that you're storing stuff in is a binary tree? By the way, I represent that using this binary tree node, and it's got a parent, and it's got a left child, and a right child, et cetera, right? I am leaking information to the outside world by making this public. Right? Make it private, okay? You can have whatever you want that violates the design of the object, of the class or whatever, as long as it's private. If it's convenient, yeah, go ahead and use it. Right? This is very convenient because I'm going to use it not only here, but I'm going to use it down here now. Right? How am I going to use it? Find the node. If it's equal to null, now here it will be an if statement. If u is equal to null, my job is done. It is not in the tree, and so I'll immediately return false. Okay? I've taken care of all cases like this, right? Oops, there we go. Where it doesn't exist. Let's find out if it works, right? Down here, otherwise I'll return true just to get it to compile here. Let me come over here to this demo. And I've got this large binary search tree already pre-built. It looks like this. Right? I want to go ahead and remove that element. So t dot remove, what was it, 13? And we'll go ahead and print it before and after. There we go. Did I show you this? Did I talk about this last time, this TXT environment? Okay. Let's go ahead and run this. And I will take it, and it's going to actually produce two diagrams here. Let's go over here to the PDF, and we'll see a before, and we'll see an after I recompile these things. Right? Oh, no. Okay. Recompile it from scratch. Oh, wow. Okay. Fine. Let's reload overleaf.com entirely. There we go. And cut, paste, there we go. Save, switch to PDF. There we go. All right. It just had a hiccup. I'm trying to delete 13. Should it have an effect on the tree? Nope. Still works. Okay. So I'm convinced that at least those cases work. Now, what about 12? Well, first of all, guess what? You have to find it. Right? We've already taken care of that step. Once you've found it, though, we're going to observe that what type of node is 12 here? It has no children. So it is a leaf. How do you delete a leaf node? Any suggestions? What if I just sever that connection right there? What would end up happening to it? Yep, it would disappear because of the garbage collection, right? The garbage collector would take care of the rest of it. Okay, so I need to take care of the situation where we're deleting a leaf. I want to know, is u a leaf? If u is a leaf, then I will simply just make the parent point to null. u.getParent, right, dot get parent dot set left child or set right child, I'm not sure, to null. Right? So I've got a couple of questions here. Right? So do you see this chain? Right? This is a really nice chain because this is kind of like what's called a fluent pattern, where you can chain things together. You've seen this before with string builders. String builders, append, dot append, dot append, dot append. Right? You can chain all those things together for a more complex operation. This one I'm saying, well, I need to delete you. So I'm going to go ahead and get my parent. Right? Oops, two parent. I don't need that. There we go. Right? I'm going to go ahead and get my parent, not my grandparent. Right? I will get my parent, and I will set its left child to null. Except that over here, let's rewind this. 12 is a left child, but what happens if I deleted a node that was a right child? For example, what if I had deleted 28 instead? That's a right child of its parent. Yes, it's a leaf, but I need to make sure that I sever the right connection. So let's come back over here and write some more pseudocode. If U is a left child of its parent, then I will go ahead and sever the connection at the left child. Else, if U is a right child of its parent, right, then I will say U.getParent, oops, parent dot set right child to null. There we go. Now, I've got a lot of blanks to fill in here. I've got questions. Hey, U, are you a leaf? Right? Hey, U, are you a left child? Hey, U, are you a right child? All three of those questions, who did I ask those questions to? To U, right? The leaf. Not U as in Y-O-U, but U as in my variable name here. Sounds like who should be answering those questions? The binary tree node itself, right? Just like we, for example, did we put it? Yep. We asked the question, do you have a left child? Do you have a right child? We can go ahead and rephrase these questions and ask, are you a left child? Is left child? Is right child? So now, are you a left child? Let's fill in these blanks and make sure that you immediately get rid of that so that you're not copy-pasting. All right? How do I know that you're a left child? How do I know if I'm a left child? Right? Yeah, go ahead.
You could return this parent get left child or something.
Get left child. All right. So if my parent's left child is equal to me, how do I say me in Java? This. Right? There we go. And I am using equals equals here because I do want to know that they're the same thing in memory. Right? I don't want to know that, well, there's that node over there that contains 42, and there's that node over there that contains 42. They ain't the same nodes if they're different in memory. Right? Is there anything else that could go wrong? How do I know that I can get the left child of my parent? What if I don't have a parent? If this dot parent is not equal to null, and this dot parent is equal to this, then I will return true. Right? And I'm just going to return that expression right there. Right? I am not a left child if I don't have a parent. If I don't have a parent, who am I? The root. Right? So can I be a left child? No. Can I be a right child? No. I'm at the root. Right? Okay. And by the way, you don't need to use get left child. You can say left child. Now, why is that? Why don't I have to use my getters, my setters? I'm in the class. Instances of the binary tree node can see the instance variables of other instances of the same class. Okay? If you want to, you can go ahead and replace that with getters, but no need. How do I know if I'm a right child? My parent is not null. I am not the root. And my right child is equal to me. Right? Did I give you the riddle to express this? Brothers and sisters, I have none, but this man's father is my father's son. Who am I? Or who is it? No? Okay. It's a fun little riddle. This guy walks up to a portrait. And he's looking at this portrait of this other person. And he says, I know this man. I know who this person is. He says, brothers and sisters, I have none. In other words, this guy is an only child. But this man's father is my father's son. Who's in the picture? He is. All right? So I'm going to go ahead and get my parent to get myself to see if that's me. All right? That's what this is doing right here. All right? All right. So are you a left child? Are you a right child? Now I can replace this. If u dot is left child and u dot is right child. Now, strictly speaking, do I need this second if statement? You're either a left child or a right child, or, careful, neither. What if you're the root and you're a leaf? That means you've got a seed, so maybe I do want both of those. I don't know. That's a corner case that we'll think about. All right, we'll come back to it. How do I know if u is a leaf? It would be really nice if it told me is leaf. Okay. Go ahead and make it. Right. Is leaf. Now, how do I know that I'm a leaf? It's not to do with my parent at all. What is it? If I have no children, right? So how can we express that in other things we've already got? This dot has left child if I do not have a left child, and this dot has right child. Right? Not this has right child. There we go. And return that. There we go. Am I a leaf? So I do not have a left child, and I do not have a right child. Now, most of you are going through 235 right now, so De Morgan's Law. How could I simplify this? And I'm putting simplify into double quotes here, because is it simplify? What happens when I pull this negation out front? What happens to that and? Becomes an or. From the perspective of logic, that's simplified because I have factored out a negation. But from the code perspective, is it simpler? It is not the case that this has a left child or it has a right child. That doesn't roll off the tongue any easier, right?
And it doesn't seem to make sense.
It doesn't seem to make sense, but logically it does. Right? I like this better. Right? Okay. Again, whatever code is easier to read is probably the better code. All right. So let's go ahead and come back over here. And I want to make sure that I'm deleting leaves correctly. Right? Let's go ahead and delete a whole variety of them. Let's delete 2, 12, 28, and something over here, 85. 2, 12, 28, 85. So on my demo here, 2, yeah, go ahead.
Just something else I was thinking, we are probably going to have to add it to those corner cases eventually. We could use the same code for is leaf or is seed if we wanted to, if it doesn't have children and it doesn't have parents.
Yes, we could use that as we could have is seed. Unfortunately, I don't think that seed is actually a standard. That's just my thing that I stole from a student many years ago. That I said, what would you call this thing? And he, it's a seed. Wow, that's obvious, right?
You can do whatever you wanted to call it, but it's just something to help that corner case.
Right. What I'm going to do is I am going to print this, and tixie after each iteration because I want to make sure that all of those leaves are deleted correctly. Let's run it and see if it works. And now this will end up producing a whole bunch of diagrams. Right. Let's go ahead and come all the way up here. You see how useful like a tool like this is. Right. Switch over to PDF, recompile it. It's going to be a little bit smaller. There we go. All right, so there's the original tree. I want to delete 2. Did it work? 2 is now gone. I wanted to delete 12. 12 is now gone, right? It was, oh, sorry. 12 is now gone. There's the third one. Then I deleted 28. Remember, 28 is right here. And now that's gone. That seems to work. Is anything else changing, screwing up? Nope, not yet, anyway. And then finally 85, and 85 is gone. Okay? Now, strictly speaking, everything is going to work here, but what about those references in the binary search tree node here? Binary search tree node, right? The parent's child has been changed to null, but what about the child's parent reference? Right? That's still being held on there. That is a potential memory leak, because when I eventually delete that one, is the garbage collector smart enough to realize that I should also, collect this one over here? It is, but it is something to think about if you don't have a language with automated garbage collection. Okay? All right. Wonderful. I am convinced that this works. Let's go ahead and check these off. Check, check. What about 45? First of all, you have to find it, right? Once you've found it, how do you go about deleting it? Now, what I want you to do is I want you to focus just on these 3 nodes, first of all. And tell me about 45. Does it have both of its children? No, it only has one child. It's not a leaf, right? We've already taken care of that possibility, but there's only one child. So what could we do to end up deleting these things? Well, the way that I want you to look at this is 40, 45, and 49. If there's only one child, what do you actually have here? A linked list, at least for those 3 nodes. How did we end up deleting from a linked list? We simply circumvented this node right here. Right? And that's what we're going to do here. All I'm going to do is, sever this connection and sever this connection. Right? Actually, I don't even need to sever that connection. Let me undo that. And then I'm going to make this refer to that one. Right? I'm going to circumvent it. Okay? All right. How do I know that that is the case? It's not a leaf. It exists, right? So else if u has one child, right? Dot, dot, dot. Now, is it going to matter if it's a left child or a right child? I don't know why it auto-completes that. Right? It is. 45 here is the right child of 40. So what we'll do is we'll make 40's right child point to 45's, it's 45, yeah, 45's right child. Right? Or maybe it was a left child instead. Right? If we wanted to delete, say, for example, let's look at another example here. I don't know. Do I have one? 49 here. Right? I would end up setting 45's right child to 48 instead. So I have some additional checking here. Right? If u dot has left child, if they don't have a left child, else if u dot has right child, right, and they don't have a right child, then let's go ahead and map this out. So if u does not have a left child, that means that it must be that it must have a right child, right? So u must have a right child. Right? And let's go ahead and remember this over here too. U must have a left child. Dot, dot, dot. Right? Dot, dot, dot. Now, why is that the case? Because I'm using these conditionals here. I've already taken care of the fact that it's not a leaf, right? What if it has both children? Don't worry about that. We'll take care of that later. Right? What we know now is that it has one child, right? And it has a right child, okay? We know down here is that it has a left child and it does not have a right child. So let's focus on this case right here, that it does not have a left child. In other words, the case that I'm working on right here, where I'm deleting 45, okay? What do I end up doing? I set its parent's right child, because I know that I'm a right child, to its right child, or it could have been its left child. Which one is the case? All right. So help me out. Let's map this out in just pseudocode. You must have a right child, so make u's parents right or left. Which one? Right or left child. Point to u's right child. So which one is it? U dot get parent dot set right child to u dot get right child, or is it, copy, is it the left child? That's going to be another check. Which one do you have, right? Because I know that I'm an only child at this point, okay? No, I'm not an only child, but I have only one child. That's it, sorry. Otherwise, I'd be a leaf, right? So which one is it? Well, it's whichever one it was, right? Do you have a left child or do you have a right child? No, wait, what am I doing? I always set the right child. This is the one I want. Do I set the left or the right? That's what I want. Right? So how do I know to set the left child instead of the right child? What am I? Right? If u dot is left child, then I need to replace it. And I will replace my parent's left child with my right child. Right? Else if u dot is right child, I will replace my parent's right child with my right child. Okay? Now let's cut and paste this and change it because it's all going to be different on the other side. Make use parents, left or right child point to use left child. There we go. And I will change this to a left, and I will change this to a left. There we go. And if I am a left child, then I set my parent's left child to this. If I am a right child, then I set my parent's right child to my left child. Now, is there an easier and simpler way to do this? Yes. Write out a logic diagram, right, where you've got this big truth table and find the simplest way of doing it. The way that I would do it in code is probably to grab either the left child or the right child, and then I would just have this one simple piece of code here, right, and then set it to from U to W or something. Right? Let's see if this works. Come over here, and instead of removing those, let's remove 45 like I was going to do. Right? Let's remove t.remove 45 and then print it out. Let's just make sure that that works in isolation first of all. Right? Okay, come over here, and I'm going to get rid of all of these diagrams. There we go. Switch, recompile, and remember I was getting rid of 45, right? There we go. 45, 49, then the 48 is hanging off of it. Looks good to me. Except that, remember I'm keeping track of parents, right? So 49's parent, what should that be? What should that be after this operation? 40, right? But is it? I'm not able to see that in the diagram, but it's not. It's actually still pointing to 45. Why? Because I never reset its parent, right? So whichever one you're doing down here, let's take this one for example. U dot get right child dot set parent should be use parent. Get parent, there we go. So to understand this, let's come back over here to my diagram. I did this, right? I made sure that 40 was now pointing to 49. But what is 49 pointing to as far as its parent is concerned? Still 45. What do I need to do to that? I need to make sure that it's pointing to the parent. This is just like a doubly linked list. If you circumvent 45 from the left to right, you need to circumvent it right to left. Okay? And let's do it over here as well for this case. Not right child, but u dot get left child, set its parent to use parent. There we go. Now it's completely cut out. Okay? Still, it should still work. I'm good not testing that. Okay. Now we come to the hard one. Let's come over here and let's erase all this stuff and take us back to square one here. And I want to delete 50 now. Oops, too thick. Okay, well, I'm looking at both of its children, and could I make 40 the brand new root? I could do something like that, and what would it look like though? 40 would have two children here, 40 and 45, dot, 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 all the way down here. But now 60 needs to go somewhere, right? So 60, 3 children. Does that sound like a binary search tree to you? That's not a binary tree at all. Okay. Well, wait a second. 60, that only has one child. I could go ahead and promote that up, right? So if I get rid of 45 here, I could put 60 up there, and it only has a right child, 90, and then it can take over this 40 over here. That'll work. Everything hanging off here, everything hanging off here. Except that, what if it wasn't like that? What if there were an entire tree hanging off of there? I'd have the same problem. All right. So what I want to do is rethink this. First of all, I'll go ahead and take 50 and put it off to the side here. That leaves a little bit of a gap, right? I don't want to disturb this tree so much. If I delete the root, right, that's like chopping off a tree at the root. That's killing the tree. We want to only trim the tree. We only want to take off maybe a leaf node or something like that, right? So I want you to concentrate on this left subtree here. What is a node that I could take out of this tree and move it up here, and it would still be a binary tree? Remember, everything over here has to be less than it. Everything over here has to be greater than it. So if I'm looking at everything that was less than this guy up here, then what would be guaranteed to be greater than everything right here? Go ahead and identify one. Could I put, so for example, could I put 20 up here? No, why? Because 40 is greater than 20, and it's on the wrong side. Could I put 48 up here? No, because 49 is greater than that. But what about 49? I could put 49 up there, right? Go ahead and get rid of it just temporarily here. We'll worry about that in a second. But otherwise, everything over here is less than 49. Everything over here is still greater than 49 because I replaced it with something from the left subtree. Right? Now we have another problem. I've just, moved the responsibility. Now I need to delete 49 because I don't want duplicates. Right? Can I easily delete that? Yeah, by moving 48 up. Okay? Now let's rethink this from the top. What was it about 49 that made it possible to put it up here? What would you call, look at all these elements. What would you call 49 among all of them? The maximum. It would have also have worked to look at the right subtree and chosen the minimum over here. Right? So how am I going to do this? Well, first of all, find it, right? And if it has two children, then I will go to the left subtree, find the max, replace the node with the max, and then delete the max. Right. So go to the left subtree. 1, 2, find the maximum. 3, and then 4 here. 4-step process here. Right. Going to the left subtree simply just means if I'm going to delete 40, I'm going to go ahead and establish a current node and go down here to 40. Now tell me, how do I find the maximum value of, now that I'm in this subtree right here? Where's the maximum value going to be? Just keep going right until there's no way that you can go any further. Okay? So find the max by simply just going right until you can go no further. Replace it, well, that means I'm just going to take whatever's stored in here and move it up here. All right? Delete the max. Let's think about this for a second. Suppose that this is the maximum node. Now, if it's a leaf, we're good. We know how to do that. If it has a left child, we know how to do that. We just took care of it. Right? If it has a right child, we know how to do that. But what if it has both children? A left child and a right child. Is this possible? What did I say? This is the maximum. But it has a right child? R is greater than maximum, so therefore, by contradiction, right, if you're going through 235 right now, that was not the maximum. By definition, the maximum will not have a right child. Otherwise, what would you have done? You would have just kept going until it didn't have a right child. And there's where the maximum is. So, 4-step process here. Let's see if we can get it done. Right? Else if. Right? Do I need an else if here? Probably not. Right? It is not a leaf. It has both children. So, else. Right? Has both children. ... Both a left and a right. So 1, go to the left child, dot, dot, dot. Right? How do I know that I can go to both the left child? Because it has both children. I've already established that through this logic. So binary tree node, T, current, is equal to u dot get left child. 2, keep going right to find the max until there is no right child, dot, dot, dot. What kind of a loop do you want to do? A for loop? Do you know how many iterations you're going to go up front? Nope. So while current dot has right child. Oh, those are coming in real handy now. While you have a right child, go to it. Current is equal to current dot get right child. And I know that's safe because otherwise we wouldn't be in this loop. At this point, current is the max. In fact, I really want to go back and rename this to max, 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 and max. If you want to do that, go ahead. But the current is the max. So 3, replace use element with the max's element. Okay? All right. So how am I going to do that? U dot set element to current dot get element. Get element. There we go. Oh, wait a second. Do I have a setter? Let's go back and check. I don't see a setter here. Do you remember why we didn't? Because design principle number 1, make things as conservative and closed as possible until you have a very good reason not to do so, to change it. I now have a very good reason to do so. I want to change it. Right? I don't want to have to create a brand new node here. So let's go ahead and get rid of that final statement, and let's make our setter. It's going to be a void function, set element, and it takes an element of type T, element, and then this dot element is equal to element. And no return statement, there we go. Right. Now I've got my setter. 4, delete the current, which is the max node, dot, dot, dot. I know how to do that, right? Because if it's a leaf, then I do this stuff. If it's an only child and it's a right child, I do this stuff. If it's an only child and it has a left child, I do this stuff, right? Okay. So cut and paste this entire thing and repeat it down below. Sound good? No. Instead, let's rethink our design from the start. You want to remove this element, great, right? Once you know that that element exists, what if you handed that responsibility off to another function? Private void delete, actually Boolean, void delete node. Right? And what I'll do is I'll take a binary tree node, u. There we go. Because I'm going to, I called it u right here, and so I'm doing that right here. Right? Otherwise, if I find it, then I delete it. Delete node u, and I return true. Right? Right? Now, how does that help me? I now have a function here that given, and it's private, so I don't have a leaky abstraction, but I have a function here, a method that given a node will delete it. Do I have that node? Current. Delete node current. Wait a second. All right, wait a second. That looks like recursion to me. And it is. But is it unsafe recursion? Right? Do I need a base case here? Nope. Because of the logic that I've established up to this point. It has both children, right? I find the max, which I know through analysis, right, and through logic here, that is not going to have a right child. In other words, it's going to end at one of these three situations, excuse me. Right? And it's not going to end up here where the maximum is going to end up having both children, and so you have an infinite recursion. Okay? Now, I do have to test this, of course. let's come back over here and let's think about tests that we could do here. All right. Well, first of all, certainly 50. What else would you want to do? What should it look like after that? It should look like 49. Oops. 49 is now up here. But it should also look like 48 is right here. And then it has no child. Something like that. Right. Let's see if it works. Let's just go ahead and test that in isolation. Not 45, but 50, right? The root node. Let's see if that worked. Well, no infinite recursion, right? That works. Switch to the editor here, and let's go ahead and take a look at whether or not it worked. Recompile. There we go. Hey, 49 at the top, 45, 48 is now there. Cool. In fact, how could I put this into speed mode here? What I could do is I could go over here to the binary tree node, or binary tree that I built. I built it out of these elements, inserting them each one after the other. Let's go ahead and delete them in that order. Right? Let's come over here to the demo. Right? And I'm going to print it before it happens. And then what I'll do is I will have t.remove x. Right? This is, and then what I'll do is I'll print it out each and every single time. Right? This is really clever testing. Why? Because it automates it. It produces these things that I can visually look at, right? And it's going to look cool, right? Trust me. Right? If you don't think it looks cool, then nuts to you. Right. There we go. Recompile this, and it's going to take a little bit longer because there are going to be however many nodes there are that many diagrams. So we remove 50, just like I said, right? Then we're going to end up removing 40, 60, 20, 45, 90. So is that correct? Maybe, I don't know. Where was 40? There's 40. So predict what it should be. We're going to end up promoting 28 up here and deleting it, and it is. Great. Next, we're going to delete 60. So what's going to happen there? 90 is going to come up to be the new right child. There we go. Good. What was the next one? Here, I've got my tree right here. Let me tell you what the next one to be deleted is. 20. We're going to delete 20 here. And since it has two children, we go over here and get the maximum, 15, move that up here. 12 comes up to be the new right child of 12. We've also decreased the size of the tree. Right? Fast forward, fast forward, fast forward, fast forward. There, 12, and that's a seed at the end. Right? I don't know why it's printed twice. Why is it printing twice? We remove 12 and then print it out down here. I don't know. I'd have to look at it. Anyway, in any case, there is probably another diagram over here, but it's not drawing anything. Why? It's an empty tree. And if you wanted to put phi in there instead, then you could. All right. So questions on that? No? All right. What we'll do on Friday is we'll talk about another tree-based data structure that you're going to explore today in your lab called a heap. So remember what a stack is? A stack is this nice organized thing where, a stack is this nice organized thing where you put A, B, C, D, right? And then you pop them off, pop them off, pop them off. The other thing with respect to memory is, if you remember from, say, 155E, if you took that, is a heap. Right? Now, when you say stack, I'm thinking very organized, right? A dish on top of a dish on top of a dish. When you say a heap of stuff, what do you think? Yeah, just a pile of crap, right? You have if you have a clothes hamper, great. I don't have a clothes hamper. What I do is I just throw them in the corner, right? And where do I end up throwing my clothes? On top of the heap. Sometimes the heap gets so large, the garbage heap or something like that, some of them trickle down and end up in the middle of the heap. Sometimes they trickle down and end up all the way down here. But in any case, if you're throwing stuff on top of the heap, that heap grows and grows and grows. Can you reasonably pull out anything in that heap? I mean, you can, but then it'll all collapse. So we're only going to take from the top of the heap, right? Top. This is going to either be the minimum or the maximum, depending on how we design this heap, okay? And then we're going to be able to throw stuff on top of the heap. Where it ends up, who cares? We're not going to be able to control that. So we're going to look at a restricted access data structure. You can work on the top and get the minimum or the maximum. You can throw stuff on, but you don't have any control over it. What is an immediate application of this? If I just throw everything into one big pile, right, and then I take off the top, I'm always taking the minimum, the minimum, the minimum, the minimum, the minimum, the next minimum, right? If I've got 10, 20, 30, 40 over here, right, and then 5 just to make sure that it's at the top, and if I take things off in order, what's the order going to be? 5, 10, 20, 40, or 30, because I put 30 on there too. Hey, what does that look like? It looks like it's when sorted to me. And what did I do? I just threw stuff on and I took stuff off. Put stuff on, take stuff off. This goes back all the way to the beginning of this course, where one of the themes of this course is that smart data structures and dumb code are a lot better than the other way around. Dumb code, put stuff in, take stuff out. Smart data structure, because now we have a way of sorting stuff. Right? We've had plenty of ways of sorting stuff, but now we're doing it with a smart data structure. Right? We'll see that on Friday, after you've experienced it in your lab.